All right, moving on from valence bond theory to a more sophisticated molecular bonding theory, we run across molecular orbital theory. Now, the basic idea of molecular orbital theory is that we go away from thinking about, so if we imagine here the nucleus of hydrogen, an electron floating around the outside, and if we were going to bond this with another hydrogen atom, so we have an electron on each, instead of thinking of these as being two separate atoms with two separate atomic orbitals are going to overlap, what we do is we think about this as a system of two positive charges and then two electrons. So the entire system is going to be considered together. So instead of looking at atomic orbitals, we're going to look at molecular orbitals. Now, unfortunately, remember we had a number of issues trying to go from a one electron system in hydrogen to multiple electron systems in other atoms. And you throw in two positive charges and all those electrons, and things are going to get a little complicated from the mathematical standpoint. Fortunately, we don't have to start basically from scratch. We can take those atomic orbitals and do a mathematical function on those, which is called finding the linear combination of those atomic orbitals. Now remember, here are some depictions of the 1s, 2s, and 3s orbitals. And remember that the functions for these are wave functions. And that those wave functions can have both positive values and negative values as a function of the radius out from the nucleus. So what we're going to have to do is go back and take another look at waves for just a moment. All right, so here, and what's going to make most sense is if we take a look at just a single wave. All right, so I'm going to add a couple of waves together here. Let's reset this. All right, so as I step through this, so notice there's a wave on the top and a wave on the bottom. And if the waves are opposite each other as they come across, you see that they will negate each other. Let's see if I make that and reset this, and I'll make this a 2 minus. And we'll step through here. So the two waves are equal in amplitude. When they meet, they would cancel each other out. Now, the wave still exists, but they cancel each other out at that point. If the two waves are pointing in the same direction, all right, now when they meet together, they will amplify. So you can see how there's an amplification of the wave if the two happen to meet together in this way. All right, another way of looking at that, though, is if we look at two waves together. So here, the top wave function, f of x t, and the second one, g of x of t, those two are currently in phase. And so if we look at those, we see that the addition of those two wave functions on the bottom results in an amplification of the wave. If I change the phase of the bottom one, so this is g, so I'm going to change that to negative, so I've just basically moved the phase over. You see that now when they add together, they completely cancel each other out. And so all I did was I changed I basically moved the wave over 1/2 of a wavelength. So now if you were to look at the waves there, the peaks on one would add together with the troughs on the other, and you would get a canceling out of the waves. again, when those waves are in phase, in the top picture here, when they're in phase, you're going to get constructive interference and you're going to amplify the magnitude of that function. If the two waves are out of phase, then you're going to get destructive interference and you'll get canceling out of that, the value of that function, the magnitude of that function. Let's take a look at this from the combination of 1s orbitals on the hydrogen. So if I take a look at two hydrogen atoms, which we would normally show the bond this way, and I'm going to label these A and B. If I look at the s orbital on the one hydrogen and the s orbital on the other hydrogen, and again, I'm going to overlap these, so there's a usefulness to our valence bond theory idea. And we've got our nuclei in the middle there. Okay. If I do the negative combination here, so the linear combination means you add the two together and then you add the inverse of the second one, or the inverse of it. So here, this is, this would represent psi of hydrogen A plus the negative of psi of hydrogen B. So if we take the negative of it, that means that this one is going to have a negative phase. It's going to be out of phase. When we add these two together, what we get then is in this region in here, we get a canceling out of the phases. And so the phases would have zero value at that point. So if I redraw this, I would now have an area in the middle where there's negative electron density, and the areas to the outside would therefore then increase in electron density. Right? Because if we remove electron density from the center, we're going to have to increase the electron density to the outside parts of these wave functions. Now if we take a look at the other combination, right? And this time we'll do psi of hydrogen A plus psi of hydrogen B. All right, now this time they will be in phase, and so the result there is that in that neutral zone here, or that middle overlap zone there, you're going to get constructive interference and you're going to amplify. So the value of the function there will be greater. So now if we look back at the result of that then, here are two nuclei, we're going to put greater electron density between the nuclei where there's that overlap. And if we increase the electron density between the nuclei, that means that the electron density outside the internuclear distance is going to have to decrease. So what we've created then are two new orbitals. And this is one of the rules with molecular orbitals and the linear combination of atomic orbitals, is those atomic orbitals, if you start out with two atomic orbitals, you have to end up with two molecular orbitals. And in this case, we get one of those orbitals is going to be a net bonding orbital. All right, so this would be a bonding condition because we've increased electron density between the nucleus. And the top one in the picture here would be the anti-bonding orbital. Now, because these are regions that are directly between the nuclei, they're sigma. So the one at the bottom would be a sigma bonding orbital, and the one at the top would be a sigma anti-bonding. And we designate the anti-bonding by putting a star above there. So for a more professional looking picture of this, we'd have something like this. So again, we've got our two atomic orbitals over here on the left. the linear combinations of those, the two linear combinations, one will produce a net bonding, so that's the oval on the bottom, and then one combination will produce a net non-bonding or anti-bonding, which will be the one on the top. The other way that we usually depict this is we would put the atomic orbitals that we're going to use to create these on the outsides and put the molecular orbitals that we're creating on the inside. So here would be the 1s orbital on one hydrogen, the 1s orbital on the other hydrogen, and we would have a bonding sigma 1s, and we would have an anti-bonding sigma star 1s. So these both came from 1s orbitals on the hydrogen, the two hydrogens. And then we would just fill in the electrons like we would with the Aufbau principle, lowest energy level first. So we put one electron in here from the one hydrogen, an electron goes in there, and so if we look back up at our picture, we have populated that lower energy orbital that's between the two nuclei, that has electron density between the two nuclei. That's a bonding situation. So again, we think of energy here going up, so the bonding is going to be a lower energy than the anti-bonding. We could actually think of potentially doing a molecule of helium, He2, and then what would that look like? Well, if we took the atomic orbitals, and so the 1s on each of the heliums, and we looked at the linear combination, and we created a sigma 1s bonding orbital and a sigma star 1s anti-bonding orbital. If we go to put the electrons in here, we have 4 electrons to place, and we put 2 in the bonding, 2 in the anti-bonding. And so here you would see that those two would cancel out. I mean, the stability we gain from the bonding would be negated by the instability of filling up the anti-bonding. And so we don't get He2 to actually form because it's, the stability we might get from the bonding is negated by the instability of the anti-bonding. However, what we could do is if we did He2 with a plus. So how does this change things? Well, now we have one fewer electron for one of the heliums, which means instead of having 2 electrons in the bonding orbital, or the anti-bonding orbital, we now only have 1 electron in the anti-bonding orbital. We have more electron density in the bonding or lower energy and less electrons in the anti-bonding or higher energy. So this actually would end up creating a more stable situation. This also brings up the first thing we're going to want to do with the molecular orbital theory is determining what's called the bond order. So bond order is going to be equal to the number of bonding electrons minus the number of anti-bonding electrons. And of course, to put this in kind of the same realm of our other bonding, we divide this by 2, since we normally think of bonds as being pairs of electrons or pairs of electron density. All right, so this is looking at the linear combination of two 1s orbitals. Obviously, once we go to the the p orbitals, things are going to get a little bit more complicated. So we'll take a look at that in the next segment.